If I look like, are you okay to hear this? Everyone good? If I look a little bit confused about the way I'm presenting things, it's because usually I don't use slides. And I've prepared a few slides for this one, unusually. I don't have any live demos. So I'm very confused with what I'm doing. Anyway, because I've prepared lots of slides and I never know how long slides take, I've put a spoiler alert on the first slide so you get the takeaway. I'm going to talk about essentially where we are with the new implementation of Idris 2. That was the point of giving this talk. I've been implementing a new version of Idris for the last, goodness knows how long, about 5 years. I've started a new core implementation over the last couple of years. I realize I've never actually talked about it. I've talked about the language, but I've not really talked about how things work internally. So I thought this would be a good opportunity to tell you that, essentially a brain dump of the one most interesting idea and how it all fits together. And it's right here on the first slide. Takeaway: term and value representations are indexed by names in scope. If you're in the business of implementing a dependently typed language and you've decided to do it in a dependently typed language, the thing you have to do up front is decide to what extent can you use the type system to help you. There's a lot of choices you could make, like do you do nothing at all and just implement it conventionally and do a couple of proofs? Do you put types, the types of terms in the term representation themselves? Do you go somewhere in the middle? Well, the takeaway is there is a sweet spot, and it's indexing terms by the names in scope, and we'll get there. We'll see what that looks like, and I'll talk a little bit about the trade-offs. This new implementation is called Yaffle. If you are British and at least as old as I am, then you may recognize Professor Yaffle from Bagpuss. Professor Yaffle is a bookend who comes to life when Bagpuss, the cloth cat, wakes up, and he is an actual know-all. So I thought it would be a good name for my functional language core, because the core knows everything about the language. Okay, so I'll give you a brief overview of how the Idris implementation works. This is just going to be sketchy. Pleasingly, a lot of the details of elaboration, a lot of the core representation, a lot of how that elaborator works has already been covered in Simon's 2 talks. So entirely accidentally, Simon has given me an introduction. So I'm totally going to back up what Simon said in those last 2 talks. I was actually also interested in Stephen's question about type-directed disambiguation of names and how it fits into this system of generate constraints and then solve them, because we pretty much do that in Idris. And the way we resolve it, I could maybe have done this on Simon's time rather than mine, but the way we resolve it is we generate the constraints, and if we get a point where we are not able to disambiguate, we just say, oh, let's solve the constraints we have and see if that helps us make progress. Anyway, so all of the things I don't say refer to Simon's talk. That's how it works in Idris, pretty much. It's implemented in Idris 2. This was partly a challenge to myself. So we had an implementation of Idris 1 that was working, and I thought, well, it's about time I tried implementing a system in Idris, like something interesting in Idris, and I realized the only thing I know how to write is a dependently typed language. So I thought, okay, well, now is the time to try implementing Idris in Idris. So we got something working, an implementation of Idris 2 and Idris 1. There's some small changes between Idris 2 and Idris 1 syntactically, small but significant. The biggest being Idris 2 is based on quantitative type theory. So it was a little bit of a pain when deciding to switch from implementing in Idris 1 to Idris 2, because we had to deal with those changes. But I did it in April 2020, and I had nothing better to do. So, it was fine. There's a silver lining to everything, I suppose. So it compiles via Shea scheme, and this is another thing I would highly recommend you all do. If you happen to be implementing an experimental programming language, which quite possibly most of you are, because that's the sort of thing we do here, I can highly recommend Shea scheme as a target. I did this as a quick hack in 2018. 2018, yeah, about then. Fully intending to move on to a proper implementation, and it still compiles via Shea Scheme. And I've been really impressed with it. So Shea Scheme is fantastic as a back end. We do turn off all of the runtime checks, or as many as we possibly can, because it's basically, I've done the type checking. I don't need Shea to do the runtime checks for me. And the performance, worth mentioning, it's very hard to put a kind of real figure on how a language performs. I'm going to assert usably fast, whatever that even means. Essentially, it means that if I ask it to do something, it will typically reply in a reasonable amount of time, like a second or so. And a lot of this, I don't know where, I think he's in the room somewhere. Andras Kovac, yeah, there he is. Thank you. Taken a lot of the ideas from Small TT, and a lot of ideas I should have taken but haven't yet from other things. And it's been marvelous for getting a system that actually runs in a responsive way. It's at least an order of magnitude faster than Idris 1, which, to be honest, is not hard. But there is a but here, and this is, I don't know if it's OHAD's fault or OHAD's responsibility, or OHAD being extremely helpful. OHAD has worked Idris 2 very hard indeed with some of his research into Frex, and has found if there is a spot where Idris 2 is slow, I think OHAD's found it, almost all of them. And we got to a point where it was just there's no way of dealing with these issues without really going back to the core and essentially doing the things that we should have done right in the first place. Because, I mean, that's what you do, isn't it? You think, oh, why didn't I do it like this in the first place? Well, because I didn't know in the first place.
But you know now.
But I know now, and I'll tell you when we get to the end what the idea is.
Do you mean fast in terms of compiling or fast in terms of generating?
Type checking. Well, type checking and compiling. And I suppose I could claim that in terms of generated code, that means it's fast because it's self-hosted. So, but I mean, these things are very hard to measure, and I'm not really the one to be the judge of it, quite honestly, because, you know, if you come along and use my language and you think it's slow, then I guess it's slow. So all of this is very hand-wavy, and this is all work in progress anyway. My feeling, and I see OHAD nodding, so OHAD feels that it's... I know when OHAD doesn't think Idris is fast enough because he comes and tells me. Sorry, question?
Yes. How long does it take to recompile Idris with Idris?
It's about 3 minutes, I think. So... it doesn't do a lot of. It doesn't do all the same stuff as Haskell and Agda and so on. But yeah, it's something like that, 3 or 4 minutes. That's I can't. I mean, that is just an order of magnitude. It's not including. Or is it including libraries? It might be. I haven't timed it for a while. I think the last time I typed make bootstrap, which is where it takes the scheme code and then builds the library so that it can build itself and then build itself. I think that whole process is about 5 minutes. So I'll time it afterwards, just to. Yeah, so I just wanted to say a little bit about the structure because I think it's worth knowing about, and it kind of tells you a bit about what my future plans are. So there is a high-level syntax, which it's just syntactic sugar for a language that doesn't really have a name, but I call it TT-imp. So it's type theory with some implicit stuff. So it's a core type theory with local definitions. It's got case blocks, so a dependent case structure, rewrite rules. We do a lot of interactive, like if you've ever done any Idris or Agda programming or proving in Coq, you know that programs spend most of their time in an incomplete state. So it's a lot of the time is working with incomplete programs. So there's interactive editing support. All of that happens at the TT-imp level, and then we kind of re-sugar back to Idris 2. Now, part of the reason I think Idris compiles a lot quicker than, say, Haskell is I think Haskell does all of that with the high-level syntax, and that's, it gives you better error message. Yeah, exactly, yeah. Which has, the big advantage is that we can experiment a lot with high-level features. Big disadvantage is the error messages we have to, and displaying things, we have to work quite hard to get back to where the programmer started, and we don't necessarily get it right. So, trade-off there. And that elaborates to QTT, which is a core type theory with quantities. So essentially that means that every variable is annotated with the number of times it can be used, which is either 0, that is it's compile time only, 1, meaning that it's linear, or unrestricted, which is, so Idris 1 would be Idris 2, but everything has the unrestricted quantity. Okay, so I'll show you, this isn't the whole of the core, this is the interesting bit of the core, as far as this talk is concerned, the interesting bit of the core. So we've got variables and binders. Binders can be either lambdas or functions. I just find it convenient to treat lambda bindings and pi bindings the same in terms of the syntax. You don't necessarily have to do that. We've got application. So application in the core language is just a function applied to a single argument. That's in the core. When we elaborate it, we do what Simon said earlier, because it works really nicely that way. We've got the type of types. Now, Idris 2 does have type in type, so please don't shoot me. We do have plans to add universe levels. It's just that nobody's shouted at me that they really want them yet, so I haven't got around to it. You know, we have there's a big constraint problem generated. There are several things in the system that say generate a universe constraint here. We just don't do anything with that information. So one day I'll get around to it. And the other thing that is new in this new representation is that we have case expressions in the core language. So what we used to do, we'd have top-level definitions that were just pattern matching definitions, left-hand side, right-hand side, and then core expressions, the right-hand side could only be, well, everything here other than case. Now that is a really nice, simple way to implement things for a while. Works very nicely. And then you try writing a linearity checker, then you try writing a totality checker, and it's a nightmare because you have to. If you give people case expressions, they will use case expressions. They're a very convenient way to program. You get destructuring lets. It's if you've written a Haskell program, you do pattern matching lets in your do blocks. We write Idris programs the same way. So. To make the rest of the system easier to work with, like to make the linearity checking, totality checking, compilation easier to work with, we've now put case expressions in the core. So, not let or let rec. No, they're at the moment. They get lifted out to the top level, which your face tells me what I'm thinking as well. Oh, we don't. A let is not a let rec like in Haskell. So they're essentially like where blocks. So we have where blocks that are lifted out to the top level. You can't have mutually recursive lets. So it's
so they just turn into applications.
So lets here just turn into they're sort of but not quite lambdas that are immediately applied to something. So I think that. I think that is an oversimplification, and that's my next step that after this current thing to deal with. Neil, you have a question?
Yeah, do you have to have a motive for your case statements?
No, you don't. What will happen, I'm not sure I want to go into these details of elaboration, partly because they're complicated and partly because they're a little bit embarrassing sometimes. We've got type-directed elaboration. So in fact, it's what Simon was talking about earlier with the, you've got the infer a thing and you know that you're inferring a thing that is a meta-variable that you will solve later. Sometimes you know what that type is, and when we come to a case expression, sometimes we know what that type is and sometimes we don't. If we don't, what we can do in the elaborator is say, pause, come back to this. So elaborate the next argument, say. And one of the things we have in our giant monad, because we have a giant monad too, one of the things we have in our giant monad is a list of the things we haven't dealt with yet. And so we might have to come back to it if we haven't worked it out. And the type checker might just have to give up, in which case it will tell you, I need you to give me a type here.
Sorry, is this the kernel or the circuit?
I'm talking about the elaborator here. So here, everything in this core language is checked. So I'm really just talking about the core representation here, because that's the takeaway of the talk. And I kind of want to say that everything about elaboration is unsurprising. It's the stuff you would do in any language with a fancy type system. Okay, so let's talk. I don't have very long for this now. So I knew I'd have too many slides. let's talk a little bit about the core representation, because that is really the key thing I want to get across, is that
QTT?
core is QTT. So, so you've got a lot of possibilities. You know, do we just do things the way we're used to and have de Bruijn indexes, de Bruijn indexed variables? Do we do something a bit fancier and have terms indexed by their types? And I spent a while playing around with different possibilities here. So I was thinking, oh, well, we've got a very sophisticated type system. We can prove large amounts of our implementation correct. And I very quickly realized, no, life is too short. What I want here is to be more productive. So I want the type checker to help me with the things that I always get wrong, and not get in my way on the things that are, at least, I'm not going to say always get right, because I don't, but the things that are more easily testable. And where we've ended up, I won't go through these details, because you've seen this sort of thing before. I'm going to skip to where we ended up. So this particular structure, or this particular predicate, I'm going to say that pretty much everything in the entire implementation of Idris 2 is influenced by this little data type. Now, what we're looking for when we're writing a dependently typed application, I claim, is finding the place where states can be illegal and make those states unrepresentable. So, you know, this is the typed programmer's mantra: make illegal states unrepresentable. So what I'm trying to do here is make it impossible to get de Bruijn indices wrong. Now, if you've ever written a program that manipulates a term with de Bruijn indices, you've probably gone home crying at some point and thrown your computer out the window multiple times. You've probably looked for libraries and tools to help you. And I think, let's say you're working in Haskell or OCaml, I know there's libraries out there that help you deal with names, right? So, and probably half of you have written those libraries, and the other half of you have used those libraries. I don't use any of those libraries. I use the type checker. And it's all this structure. So this structure is a representation, or it's a predicate that says that a de Bruijn index is correct in the current scope. So we've got the variable name, we've got its index. So this nat is
String, the name.
it's more complicated than that. It's not actually represented as a name at runtime. This name is really just for display purposes. But it's a complicated string. So it's a namespaced string. And then we've got a SNOC list of names. So these are the names in scope. The reason it's a SNOC list, by the way, is because when you write down the typing rules, you'll stick the variable on the right. This was a list for a very long time, until my former postdoc, Guillaume Allais, got really annoyed and switched all of them to SNOC lists. And he was right. So, yeah. So the zeroth variable is, n is the zeroth variable in the scope that ends with n. And if n is in scope at position I in the variable's ends, then it's in scope at position I plus 1 in an extended scope. Okay. So hopefully not controversial. Nope.
It reads as if your answer to the question of should I use names or indices is to say both. Correct.
Yes. And then I have a type checker that tells me that makes sure that the two things are consistent. So here's the other thing. If I were to represent this in the way it worked in Idris 1, which was written in Haskell, local variables had an index, and it was just a nat. That was why, or it was just an integer at runtime. So nat at runtime, it's essentially it's an integer. And then we have this proof that this index is correct in this scope. And oh. Okay. Well, that was a good moment for it to vanish, because this 0. This is a bit of quantitative type theory magic. That 0 means that if I accidentally have to use that proof at runtime, I get a compile time error. So what that means is I've proved that the name is in the correct place in scope, but I only have the NAT at runtime. So QTT, thanks Bob, thanks Connor, is lovely for this sort of thing, because it means I did a whole PhD on this and it didn't quite work out. I mean, it kind of worked okay, but we've now got to a point where we know which things are going to be there at runtime and which aren't because the quantity says so. So these are just two very little ideas I'm showing you here. QTT is useful for erasure, and indexing terms by names in scope is unreasonably helpful, and then everything works out very nicely. So what follows from that is you have to write a bit of machinery. So this is all the machinery that you have to write for term manipulation anyway. It's just that, if I let's look at weaken. So weaken is an interface is what we call type classes, and we call them. I won't go into the details of why. This is where we say, a term in one scope is also a term in some bigger scope. Or in order to do that, I might have to weaken the scope with some variables in the middle. Here's a fun one. Challenge to you. Take your Brown index representation, write a function that swaps the position of the top two variables in scope. Good luck. Type checker told me how to do it. So rather the interactive editing told me how to do it. And I know this works because it type checks. And that I don't know, I just find that pleasing. I should have grown out of how pleasing I find that by now, but I haven't. Obviously it's frustrating trying to write the program in the first place, but you know that when it works, you're not going to have any surprises. Now I promised one more thing, and I'm nearly out of time. And 5 minutes, okay. If I've got 5 minutes, then I guess I can do this almost properly. The other thing, this is the key thing that OHAD found, is about evaluation or unification. So a crucial part of the elaboration process is taking a term and evaluating it as far as we can, given the program we've got. So there might be symbols that we don't know about. So that happens during unification, and that might mean that we have to evaluate some fairly big terms. Now, what Idris 1 does is it just evaluates it to normal form, because I was experimenting and I wanted a thing to work. What Idris 2 does is something a little bit cleverer, only a little bit cleverer, in that it has heard of closures, and it's you get a weak-head normal form. But even then, sometimes it evaluates too much. So there might be something you might have a function application which it can evaluate but shouldn't. And what we don't know in advance is whether we should evaluate or not. So really simple example of this. Imagine I'm unifying 1,000,000 plus 1,000,000 with itself using NATs. Now, if I say the unification works by evaluating to head normal form and just keep going as we find out more about the term, that's going to take ages. But I already know it's just 1,000,000 plus 1,000,000, so I shouldn't need to go any deeper into the expression to do that. So we don't necessarily know in advance which of these strategies is going to be the right thing to take. So again, thanks to Thierry Cocon, possibly. So this is a glued evaluation. Again, I learned this from Andras. I should have known it already, but again, you made it clear to me, so thank you.
I borrowed the glued term, I think, from Connor.
Yeah, and so I think it's in the Epigram Reloaded paper, possibly. And I don't know where Connor and James learned it from. I think it goes back to the 90s anyway. For some reason, even though it's one of those things that even though we've known it's the right thing to do, nobody's done it in any.
What is it?
Oh, yeah, sorry. I got so distracted by that interaction that I forgot I haven't even told you what it was.
Everybody denies inventing it, but what is it?
Well, if I tell you, then okay. So glued representation. What's happening is when you've got an application node in your value, you keep the application node and what it evaluates to. That way, if the application node without evaluation is enough, it's right there, you've got it. This is good news, firstly, because it makes lots of things quicker. You can do like an approximate conversion check. But it also means that when you print out the error message, you get the thing that the programmer wrote and not the thing that you happen to have evaluated it to. So it looks a bit like this in values. So, oh look, here's an application to a spine. We've seen that today. So we've got an application node after we've evaluated it will be the function name there's actually a bit more going on here. I've simplified this a little bit, but it's the name applied to its arguments. That's its original form. And then if it's possible to evaluate it further, which it may or may not be, because we have to deal with the fact that programs could be partially written. We have things that we have programs that might be type declarations, but not the definition. So we have to deal with the fact that it might be stuck. But if it does evaluate, if it turns out we need to go further, we can go further. This core, by the way, is the giant monad. I put monad in quotes because for technical reasons, it's not quite. But think of it as a monad, it contains all of the state, all of the meta variables. In fact, all of the things that Simon mentioned. Thank you so much for explaining my talk in your talk. So all of these parts of the type checking monad, they're all inside core. And if it turns out we need to go further, we can. But it turns out a lot of the time we don't need to. Now, initial experiments, I haven't been brave enough to try OHAD's FREX yet because we're not quite there. But initial experiments are showing that this is, in the general case, very slightly slower, but in the kind of unhelpful case or the difficult cases, it's significantly faster and is removing the bottleneck.
Do you put a pair of the unreduced thing and its weak-head normal form?
It's
normal form.
It's an unreduced thing and a thunk that will give you the
A thunk that will give you
the weak-head normal form.
Weak-head.
Yeah.
Okay.
So
if you hope the thunk, you get all the way to weak-head normal form,
yeah.
not just one step.
So this is actually, I kind of skipped this, but a value is indexed by whether it's the unevaluated or it's definitely evaluated. So this, actually I've done this to make it easier to port from the existing Idris code. But the values are indexed by whether we know that they're a normal form or not. So we can look at the type and say, oh, I need to do more work on this. Or we can look at the type and say, I've definitely got the normal form here. Oh, I've definitely got the head normal form here. So I shouldn't say normal, that's really weak head normal form. Right, I'm just going to give you the lessons learned because I am out of time. That indexing names by scope, I look at it now and I think, wow, that's simple, but it is unreasonably helpful. I think it's saved us so much debugging time. It's increased the amount of frustration when writing the program in the first place, but we don't have to keep going back to the program and debugging it because we know it works. Quantity 0, wonderful idea. So we're based on QTT, so we've got 0, 1, and unrestricted. I think 1 is, academically, the 1 quantity is probably the most interesting, but 0 is so useful. I could just have QTT with 0 and unrestricted, and I would be happy. And yeah, promising feedback from early adopters. And finally, I'm just going to say we are almost compatible with Idris 2. 95% done, so I think there's about 95% to go. And so probably what we're going to do is just take the best bits of this new representation, Yaffle, and move it to the upstream Idris representation. Essentially, that's the gluing. And then I'm going to go and have some fun with Yaffle because I've been wanting to play with some more ideas of surface languages for a long time, and I'm expected to work on Idris. So I'm going to take Yaffle and have some fun with it. And yeah, you can help me have fun too if you like. Yeah, thanks. I'll stop there.
So we are getting into the break, but if people are interested in asking questions, maybe we can have 1 or 2 questions while the people.
Yeah, I don't want to keep you from your coffee, so.
I have a short question.
Sure.
What if you have add $1,000,000+1, $1,000,000-1? Is that fast, slow, or don't care?
Good question. I'll have to try that. So what I would hope is that it depends how you've written them. If it reaches a point where the two.
One step would reach to the same
Yeah, if one step would get to the same thing, depends how you've written it though. So, I mean, I think my advice would be don't write a program like that if it's taking a long time to type check. But don't doctor, it hurts one eye. Don't do that then. Yeah, easier said than done. Sorry, yes.
So a question is, one difficulty with the small TT work is that his benchmarks are sort of synthetic and ugly, most of them. So is it a problem that you can help improve on with Yaffle? Because now we have real-world programs that people care about that you can use to play with these ideas.
Oh, maybe. I mean, this is something I've noticed looking at small TT is that I trying to get the same performance as small TT, because small TT is really fast. And I think, well, part of the reason that Idris isn't quite that quick is because it's got a lot of other stuff to deal with. But also, we're not necessarily dealing with all of that other stuff well. So, we need to. There are things that we need to revisit. But yeah, having a full size system that is using those ideas is probably a good place to play. Yeah.
Hi, I'm kind of curious. So when I see these scope index things, I feel that for very simple, simply typed on the calculus, you only extend the scope one variable at a time in a very boring way. So I kind of trust that this is a reasonable thing to do.
Kind of like
but I feel that for more real life languages, you need operations like list concatenation or these kind of fancier things. And so I wonder, in your experience, what kind of list operations do you... Okay, so these are really the things. Yeah. You need inserting something in the middle is the only, and swapping is the only crazy things you do.
I've carefully chosen these to be the most complicated things we have to do.
Okay.
There's a lot of list associativity proofs.
Yeah.
And once you've done it once or twice, every one of them has the same pattern. To the extent that I would like to know how to abstract it, I guess OHAD's on the case for that as well, to be honest. That's part of the point.
I think on this thing, I don't know if you've seen it, there was a talk by Jesper Cox at Types this year that was basically trying exactly this, trying to find a fanciest representation you can do for scopes, so that you would support all these kind of operations natively. And I think his conclusion was kind of a negative one, that he actually didn't, he ended up with a data that was so complicated that he ended up in some sort of weird impossibility corner.
Interesting.
So yeah, you might want to look at that.
Because at the beginning, yes, it was a challenge.
Okay.
But once I'd got over the initial challenges, it's like, oh, it's all the same now. It's no problem.
Thank you. It's very enthusiastic that you can get away with this kind of thing. Yeah. Thanks.
All right, so I think we should probably wrap up at this point. Let's thank Edwin again and all the speakers this session.
Thank you.